Fala Lepo, Marco. Sorry, it's quite a long CV. I appreciate we're heading towards the coffee break, so I'm going to be fairly quick. I'm talking about fibre-reinforced spray concrete. And I was impressed yesterday in our workshop. There's obviously a lot of knowledge about fibre reinforcement in Slovenia. There's been some research over many years. So some of this will be familiar to people in the audience, so I'll move quickly. Other things will be perhaps new. This is what I'll talk about. It's predominantly talking about steel and macrosynthetic, which you can see there. But also there are some new materials emerging, for example, glass fibres, which are the sort of the white ones there, or even basalt fibres. So it's a constantly evolving sector. And you'll see that I'm a fan of fibre reinforcement. There are many, many applications where we can use it. I'll talk a lot about spray concrete and about segments, but let's not forget we use a lot of smaller, less glamorous pieces of concrete in our work. Cable ducts, water pipes, water sort of containers. There's a huge opportunity to be using fibre reinforcement for those structures. It makes them easier to manufacture, easier to install, less damage. And you can also be even using it, for example, for track bed. Typically quite often used for trams and so on. So lots of opportunities to use fibre reinforcement. Talking about tunnels, we've talked quite a lot yesterday about permanent spray concrete, and a key element in that is removing steel bars. Replacing the steel bars with steel fibres, and you can see some examples here showing the breadth of application. Not just hydropower projects, but also railway transportation tunnels and so on. The picture is actually from a water tunnel at Heathrow in the UK. So in terms of sprayed concretes, as I said, the trend is towards using permanent sprayed concrete. A key element in that is the use of fibres instead of using steel bars, because it's inherently more durable. And I'll come back to that with a little bit more detail later. That said, one obstacle, if you look at how this technology has been adopted around the world in the last, 30 years, should we say, one obstacle has been the question of design. How do I design it? And this is what I'm going to focus on today, and perhaps share some experiences of my own in that design. So there are two types of fibres, which I'm sure most of you know. There are non-structural fibres made of polypropylene, very short fibres, and we use that for fire protection. And then, of course, there are structural fibres. I think they're using macrosynthetic on T2DK or the Peckle tunnel at the moment. And most of the tunnels built so far have been using steel fibres. And you can see from the standards, typical minimum strengths for the material. What we're seeing now is a trend towards steel manufacturers offering very high strength steel and slightly different shapes to their fibres. I will talk about whether that is something we need or not. As I said, lots of new materials appearing. Sometimes these are not covered by codes, but we have to remember we need to embrace innovation. We need to accept that codes are always at the end. First of all, you have a clever idea. Someone is brave enough to try it. If it works, a scientist will try and work out why. It's written into a code last. So we need to balance the desire to be conservative, which all good engineers should be, and also to embrace innovation. Amongst the sort of the new materials, we're beginning to look at recycled materials. Some interesting work done in Zagreb and UK, looking at using fibres from tyres. For example, polypropylene fibres, which can be used, and they seem to give some good performance in that task of protection against fire. So interesting developments there. On that subject, you're familiar with the sort of the fire tests. You have a particular fire curve. Obviously, as we know, unfortunately, the heat that you get inside a tunnel is tremendous, very high temperatures. You're hitting at 1,000 degrees. And the problem with normal bar-reinforced concrete is that we make very good concrete. That means it's very dense. There is still water in the pores of concrete, and when you heat up a very dense concrete, the water turns to steam, and the danger is that causes an explosive spalling. Polypropylene fibers melt at around 100, 150 degrees, and that allows, or one theory is that allows the steam to escape, and hence you can see that this sample that's been put through one of these fire tests, it doesn't show that deterioration that you might expect from a bar reinforced sample. So, turning to the structural side, a lot of you are familiar with this sort of picture from a simple beam test, where you take a beam, you bend it, the concrete cracks, and then you have this residual tensile behavior, and it can go up, which is called deformation hardening, but more typically you'll have a peak, it drops, and you have a deformation softening. An issue for us as designers is, if you don't have the test data when you do your design, and typically you don't, what are the sensible numbers for us to choose when we do our calculations? What can we assume? And this is what I'll hope to walk you through in this discussion. So I've tried to gather some data from a range of projects. The majority of this is steel, but there are a few macrosynthetic examples in there. And what I'm plotting is the strength of the concrete across the bottom versus in this case, it's the first residual strength. So after the concrete is cracked and it drops down, that's the residual flexural tensile strength there. And if that, for example, was half of the peak, and the peak strength is basically driven by the concrete. The fibers don't affect that, it's the natural strength of the concrete typically. So if it drops to half, that would be the line that you see here typically. One thing to note is the large scatter. So I'm presenting data here that's from beam tests, and that has been a problem with the test for reasons I can explain afterwards, that you can get quite a lot of scatter. So that gives us some idea of the strength at that level. But if that crack is opening, we need to know how ductile that behavior will be. Will it sort of come back up? Will it continue to go down? Will it drop in a brittle fashion? And this is where you then look at the values of different strengths. A point that was mentioned, I think, earlier on is the effect of strength, that we're making some very high quality concrete. Some examples from yesterday were strengths at 7 days, I think, of 37 MPa. This is for a 25 MPa mix. At 28 days, I think it was about 48. And Wolfgang was commenting about how you test at a year and you might find it's at 60. That is not necessarily a good thing in the context of fibers. You're probably generally familiar that the idea is that you try and pull the fibers out. That gives you ductility. If the bond from the fiber to the matrix is too strong, it snaps, and we're back to a ductile material. And this can be a problem if there's sort of a mismatch, shall we say, between the fibers you have. You can see there's a bit of a trend towards a reduction in the residual flexural strength as the strength of the material increases. That's partly what's driven this tendency with steel fibers to have some of these sort of ultra-high strengths, because if you can harmonize the strength of the fiber with the strength of the mix, you resolve that problem. I look at it slightly the other way, which is, why do we need that strength? If we have stresses in our tunnel lining of 2-3 MPa, and we have a compressive strength, obviously we're talking about an average value there and ignoring bending, but we have a strength of 60 MPa, maybe we're over-designing. And that's so going back to Wolfgang's point, if a little bit more intelligent design could help us to optimize that. Creep is a subject that crops up very often. I've had the privilege of sitting on some committees where we've looked at these things, and there's a lot of debate about this. So I'm going to sort of present my best understanding of the data that we have. it's raised as an issue for macrosynthetic because, of course, it's a plastic, and we know that plastic creeps. What I'm plotting here is data from 3 different studies. This is time, and these are the results, the creep coefficient, which is measuring how much extra deformation you get if you take a beam, you crack it, and then you keep a load on it. And obviously, if it's creeping, it'll continue to move. So all concrete creeps. Now this is tensile creep. So bar reinforced concrete creeps in tension. And that's why we have coefficients in Eurocode, for example. Steel fibre reinforced concrete, that's that grey box, also creeps. And it's a similar, there was one sample with bars, which is a similar sort of area. So that creeps. Macrosynthetic fibres at low levels of utilization, so that I mean relative to the ultimate strength of your beam, if you're at a low level, let's say below 40%, which is basically where we'll always be because of the factors of safety that we have in our standard codes. If we're at that sort of normal working level, they're generally creeping in a little bit more, maybe 1.5 times, but it's not the same order. The triangles are, again, macrosynthetic fibers, so they're in the same range. And then the third study, at a utilization of 40%, they actually found, if you look at this, these dots, they found there that the steel fibers on that occasion performed as in the same way as the macrosynthetic. Creep's quite a complex process. It takes quite a while to digest the data. But my overall conclusion from that is that yes, macrosynthetic fibers creep more than steel fibers, but not so much more in the conditions we're talking about that it's a problem. If you have a different situation, if you're working, for example, in the Middle East, you've got an ambient temperature of 30 degrees, your creep is temperature dependent, of course, you've got some extreme loading, then it's something perhaps to worry about, but not in most cases that we're looking at. Durability, to cut a very long story short, fibre-reinforced concrete of all types is much more durable than bar reinforcement. We know what the problems are with reinforcing concrete with steel, and the attack is very often related to the steel rather than to the concrete itself. So if we assume we can solve the durability of the concrete, if we use fibres, we have inherently a more durable material. We can use fibres that don't corrode, basalt, macrosynthetic, for example. If you have a steel fibre in an open crack with water, oxygen, that steel fibre in the crack will corrode, but the rest of the fibre is embodied or embedded in the concrete. The fibres where the crack is very narrow won't corrode. So to give an example of the experience that we've had in Scandinavia, where we have tunnels with fibre-reinforced spray concrete for about 30 years really, the overall conclusion is that you can apply the normal sort of exposure classes that you see from Eurocode, and the Norwegian Road Authority has then set minimum thicknesses for their spray concrete linings to meet the durability that they need, which is typically 100 years. And you can see that generally ranges from 80 millimeters in a standard case, but if it's a subsea tunnel where you've obviously got a more aggressive situation, it's more like 100. And that's a sample from one of these tunnels. It's 22 years old, and it's in very good condition. So it's very durable. If we move on to design approaches, there are different ways of looking at that, but essentially, in my mind, we're adding the fibres to ensure that we have a ductile material. Plain concrete is brittle. With fibres, it's ductile. We get some bending strength, but if we've got big bending moments, we need to have bars. So that's the summary. People have looked at different ways of designing. Maybe they assume that there's zero tensile strength. That's very pessimistic. We know, and some of you may recognize this from the German guideline, that you have that peak, you have some sort of tensile capacity because we've put all these fibres in. So we need to make use of that just making use of the peak tensile strength of concrete. Again, we're not gaining anything. So overall, I would say that the best approach is to be using the model code produced by FIB in 2010. It's consistent with Eurocode 2, so that's great. That fits with our normal calculation process, and it's a very well explained method, and you can then create an interaction diagram I'll show you later with the capacity of the fibres added either on their own or together with bars. Still have the question in my head, what numbers can I use? So I'll try and sort of walk you through that. You basically need to be assuming what sort of residual strength you have, and I've called those parameters A and B. If you have test data, you have the answer already. If you make an assumption in a design, obviously you need to test during construction to validate that. But this is sort of an interim, a first guess of what is reasonable. And again, putting this data together, you can see that it's quite reasonable to assume that the first residual strength, FR1K, is about half of the peak strength, which is based on the tensile strength of the concrete itself. And then if you look at that slope, basically, and this is the way the specification is set out in the model code. They have different classifications, A, B, C, D, E. And basically, if the strength towards the end of your beam test, the FR3K value is between 0.7 and 0.9 of the first residual strength, then that's a class B. And you can see there's a limited data here, but that's a reasonable assumption to make. These are numbers that are achievable by the contractors with typical mixes. So again, I'm plotting obviously a variation with the strength there. So in terms of designers, we have specifications to tell us what minimum requirements typical fibers should comply with. We have a design method. We can turn that into a performance-based specification for the contractor. So we're telling him a certain sort of compressive strength that we need, and then we tell them what the first residual flexural strength should be. So that's 1.7 in this case. And then in terms of this slope, we call it a class B. So that means that the minimum strength at FR3K would be 0.7 times 1.7. So a nice simple way to specify a performance requirement for the contractor. What does that mean when you turn it into capacity in your design? You can see from the equation here that the tensile strength you're allowed to use in design by these codes is actually very small. So the consequence of adding the fibers when you look at your capacity curve is very small. And in that sense, as I say, you're sort of guaranteeing a ductility, but you're not really adding a bending capacity. So perhaps the simplest thing to look at here is the black curve. So this is if we had nothing, no bars, no fibers or anything, and we add the fibers, you've got this little dotted line. So you can see there's a little bit of gain. You sometimes have a case of hybrid where you have steel bars and fibers, and then in that case again, you can see that the difference between just having bars and then adding fibers with the bars is very small. So it's a small gain in that sense for the bending capacity, but the real win for us is we have the confidence that our material is a ductile one, not a brittle one. Rock tunnels, slightly different. We're generally working off the Q system with any energy absorption, so I'll skip over that, but happy to talk about it later. If you have something quite complicated, here this is some work I did a few years ago looking at segmental linings, looking at, so it's a purely fiber reinforced segment for a metro tunnel, and you have the governing load essentially it's the ram loads as you push the TBM forwards. You get these very high concentrations of compressive strength, and then you get tensile splitting tends to appear in between. So we can model these using sort of the fracture energy approach inside a typical sort of finite element, finite difference code. But here you have to calibrate your model based on the data you have. So you're looking at the energy, which is the area underneath the curve, this low deformation curve, and that's how you calculate the response of the concrete. So you can use that as a way to check your designs if you need it. Specifications. So the good thing is we have quite a lot of information on that. If we're looking at residual flexural strengths, it's probably best to be using the notched beam test 14651. Panels, you can use RDP, the round determinant panel, or square panels, which we discussed a lot yesterday. If you look on the ITA website, you'll find that we've produced several reports. There's 2 reports on precast segmental linings, which has a lot about general design of fibre reinforced concrete, and then also in working group 12, we've looked at sprayed concrete as well. Great to see some more focus on the subject of embodied carbon and sustainability in tunnelling, and great also to hear how much progress the cement industry is doing, and seeing that the other suppliers are also taking this issue very seriously. I firmly believe that this is work that we as engineers should drive, because we know what solutions are viable to deal with this problem. Using fibres, as you can see from this picture, is a very beneficial step in reducing the embodied carbon. So this is a typical segmentally lined tunnel. It's a metro tunnel, 6.5 meter diameter. If you have a typical bar reinforcement, you can see how using steel will reduce that significantly, maybe 10%. Macrosynthetic, if you can use that, will reduce it even more. And the hybrid here is a combination of the macrosynthetic with perhaps a cage just underneath the ram shoes, which is also quite a good option, very effective structurally. So to round off, hopefully I've explained that this is very much proven technology. It is, as I said, many applications for segments, precast units like cable ducts, water retaining structures, and also sprayed concrete as well. Lots of information published out there, and we have it embodied in certain specifications. So it's quite helpful to give us a foundation that we can work from and apply this to our projects. And that is everything I was going to say. Thank you. Follow up.